What led Newton to his law of gravitation? Is it a falling apple? Or is it the falling moon? Before we begin our discussion today, let me quickly recall that in the previous session we discussed Galileo's double inclined plane experiment that eventually led Newton to formulate his first law of motion. In today's session, we're going to discuss how Galileo's single inclined plane experiment that led Newton to a path by which he arrived at his second law of motion as well as his law of gravitation. Let us consider a wooden plane which rests at an angle theta, as you see it here. A bronze ball is allowed to roll down along the plane. Subsequently, Galileo measured the time required for the bronze ball to roll down to the ground starting from different initial locations. By doing this experiment, Galileo found out that the distance traveled by a falling ball on an inclined plane is proportional to the square of the travel time. The experiment was repeated by Galileo with a different inclination angle, as you see it here. However, he came to the same conclusion. By repeating the experiment for many different angles, Galileo made a proposition that if one were to throw the ball from the Leaning Tower of Pisa, even then it would follow the same rule. This led Galileo to formulate his law of free fall, which states that the distance traveled by a falling body is proportional to the square of the time it takes to fall. So if the travel distance is d and the required time is t, then d is proportional to the t square. Now if you look carefully, then you realize that Galileo's law of free fall is the same as Newton's second law of motion, but for a constant force. You may have read about the letter which was written by Isaac Newton to Robert Hooke of the Hooke's law, in which Newton wrote, "If I have seen further, it is by standing on the shoulders of giants." Here he was referring to the work of Galileo and Kepler. Incidentally, in 1642, Galileo passed away, and in the same year, Isaac Newton was born. In order to appreciate the path by which Newton arrived at his second law of motion and also the law of gravitation, let us consider a body which moves by a distance delta x in a time interval delta t. Galileo's law of free fall then implies that delta x is proportional to delta t square. Let us denote the proportionality constant by the term beta. On the other hand, Galileo's law of inertia states that a force causes change in the motion of a body. Newton realized that the change in motion really implies change in velocity of the body. Clearly, the force is proportional to the change in velocity, that is, the force is proportional to the acceleration. In other words, Newton came to the conclusion that the constant beta in the law of free fall is proportional to the moving force acting on the body. Having realized the role of a moving force in causing an acceleration of a body, Newton proceeded to find an answer to the question, why does a body, say an apple, fall? Given the apple was at rest initially, a falling apple means there is a change in motion or change in velocity of the apple. Newton then asked, what is the moving force that causes the change in velocity of a falling apple? Further, Aristotle told us that Earth is a sphere, By considering the diagram as you see here, it appears that the apple always falls towards the center of the earth. Then the question is, why does the apple always fall towards the center of the earth? Newton realized that the moving force is due to the matter content or some property of the earth itself. He gave it a name, gravitational force of the earth. This explanation then led Newton to ask few follow-up questions. Does the gravitational force extend beyond the length of an apple tree? Or does the gravitational force extend up to the orbit of the moon? Now there are two possible answers, either yes or no. Newton then asked, if not, then why doesn't the moon move in a straight line as implied by the Galileo's law of inertia? Or if the answer is yes, then why doesn't the moon fall on the earth as like an apple? At first glance, these two possibilities appear to be contradictory to each other. In order to resolve this dilemma, Newton then proceeded to find the required force to keep the moon in its orbit. Let us consider, starting from the point A with speed v, the moon in time delta t would reach a point C if there was no force acting on it, as per the law of inertia. Now, if a force is acting on the moon to keep it in its orbit, then the force must cause the moon to fall by a distance bc, as you see it here. The law of free fall then implies that bc equal to beta times delta t square. Using Pythagorean theorem, now we can establish a relation OA square plus AC square equal to OC square. We may identify OA and OB as the radius of the orbit. Now for sufficiently small time delta t, we can neglect the term delta t to the power 4. Now a simple calculation implies that the required force to keep the moon in its orbit is proportional to b squared by r. On the other hand, Kepler's law implies that the orbital period capital T squared is proportional to the r cubed. Again, by using simple calculation, we can express the gravitational force as proportional to the 1 by r square. This is the celebrated inverse square force law of gravitation by Isaac Newton. In summary, Newton managed to resolve the dilemma by discovering the inverse square force law of gravitation, which causes both the apple and the moon to fall towards the earth. But for the case of the moon, the amount of fall is not sufficient for the moon to land on the earth. It seems all good. However, there is a catch. Newton had realized that he had made an approximation to ignore delta t to the power 4. Does that mean inverse square force law of gravitation is an approximation? I hope you have enjoyed today's session. In case you have any question, comment or suggestion, please feel free to write them below in the comment section. And if you like to follow the physics discussion here, then you are welcome to subscribe to this channel.